Welcome everyone. In this video we will derive the formula for finding the moment of inertia of a uniform rod about its center of mass. So let me draw the rod first. It looks something like this. We are given that the total mass is capital M, the total length of our rod is L, and as I said, this is a uniform rod, which means that the center of mass is at the middle of this rod. So this distance is L over 2 and this distance is also L over 2. We want to find the moment of inertia about this center of mass. So the question is, what is I center of mass? To carry out our calculations, we will use the definition of moment of inertia. If I define an arbitrary point like here at a distance x from the axis which we choose as the x equals 0 direction, from that direction, then the moment of inertia, the infinitesimal moment of inertia, would be dm, the mass of that infinitesimal, the infinitesimal mass, the mass at that point, times x squared. This is by definition correct. Now, to get the center of mass moment of inertia, we will integrate both sides. And we will actually have the limits, but to have limits that help us, we need to get rid of this dm and write it in terms of dx, perhaps, okay? So how could we do it? Well, we know that dm over dx equals the density, which we can call lambda for this case. Okay, mass over the distance gives you the linear density for the rod. And I just said at the beginning that this is a uniform rod, so this density is mass, capital mass, the total mass divided by the total length. Which means that if we solve this for dm, the infinitesimal mass, dm equals capital M over capital L times dx. So we can substitute this guy here. Actually, let me write it on the new line. So on the left, from the addition, from the integral, we will have the center of mass, moment of inertia. And on the right, we now have m over L x squared dx. Now it makes sense to put the boundaries. And what will the boundaries be? From 0 to L, right? No, this is not correct. This does not work. The boundaries will be from negative L over 2 to L over 2. Because notice this. We choose the axis of rotation as the 0. So it is the point, it is the line at which x equals 0. To the right, x values increase. To the left, they decrease. So we don't start from 0 and end at L. We start from negative L over 2 and at L over 2. This is the most crucial part of this derivation actually. Now with that being said, we can now take this integral and divide by L is a constant. So we take it out. What is the integral of x squared dx? It is x cubed over 3. And we have the boundaries. Now we are going to use the fundamental theorem of calculus. We are going to substitute these values so that we have ml 3l, let's say, l cubed over 2 cubed, so 8 minus, this is the first term, minus, we're substituting this guy at this time. We have m 3l negative l cubed over 8. Notice that this and this, they become positives. So I can erase this negative sign and make this a plus. Now we can add these guys. We have 2m L squared over 24. Notice that I cancelled these L's. And we can simplify this further. 2 divided by 24, that is 1 over 12 ml squared. And this is our final result for the moment of inertia of a uniform rod through its center of mass. I hope this derivation was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.